What is 2 plus 1 over 4 plus 1 over 4 plus 1 over 4 and so on times 3 plus 1 over 6 and so on? How do we evaluate this multiplication? How can we make sense of this? We could try expanding this, but it seems to only make things more complicated. Maybe instead we could look at the terms one by one. So we'll call the term on the left a, and then we'll notice that a plus 2 is the denominator of a minus 2. So we can just replace that with a plus 2. And then if we do a little algebra, we find that a equals root 5. So the left side is just root 5. And similarly, we can find the right side to be root 10. So the product of these is just root 50. Or 5 root 2. But this answer doesn't feel very satisfying. We started with numbers in this format, so it would be nice to get a result in the same format. And more generally, what if we want to multiply any two numbers in this form? Or add them, or subtract them, or divide them? In this video, we will develop a method to do just that. Numbers in this form are called continued fractions, and they solve a problem of regular fractions. Regular fractions are great for rational numbers, but they can't be used to represent irrationals, at least not with integer terms. But we can represent irrationals, such as root 5, using a continued fraction, because the infinite amount of terms allow for infinite precision. This is just like how we can write root 5 as a decimal. We need infinite digits, but it can theoretically be done. And we can think of this infinite decimal as a sequence of finite decimals that get closer and closer to root 5. And we can do the same thing for continued fractions. This sequence approaches root 5. For each step, we just add in the next term. And if we evaluate these, we see that yes, they do get closer and closer to root 5. And this goes for any continued fraction. The value is the limit of this sequence. And to make notation a little easier, we'll call this a, and then each of the terms a sub 0, a sub 1, and so on. And so if we have a continued fraction a, and another one b, then we can find their product by taking the product of these terms. This sequence will approach the product of those continued fractions. So back to our example, earlier we saw the sequence for root 5, and then we can also find the sequence for root 10, and if we multiply these, we get a sequence for root 50, and yes, this does approach root 50. And to understand this a little better, let's find the next term in this sequence. So we'll find the next root 5 term. To evaluate this, we'll start in the bottom right. 4 plus a fourth is 17 fourths. Then we take the reciprocal to get 4 17ths. And then we add in 4, and then take the reciprocal, and then add in 4, and then take the reciprocal, and then finally add 2. And we get 682 over 305. So we can add this to the bottom of our sequence for root 5. But finding this value was kind of tedious, and as we get further into this sequence, the process is just going to get longer. Luckily, there's a better way we can do this. We just need the previous two terms. So we'll take these two terms, and the next term in the continued fraction is 4. So we will use that. If we take 38 plus 4 times 161, we get 682, the numerator. And we can do the same thing with the denominators. And this gives us the next fraction in our sequence. And we can do this with any continued fraction. If we split a sub j into its numerator and denominator, then we can find the numerator based on the prior two numerators, and the same thing with the denominator. This is very similar to the Fibonacci sequence. We're using the last two terms. The only difference is that we have this a sub j term that's being multiplied by the prior. But the case where that a sub j doesn't matter, when the continued fraction is just all ones, then our sequence just uses Fibonacci numbers. And here's that sequence a little further. Now, going back to our problem, we found the next term for root 5. Let's do the same for root 10. We just need the prior two fractions, and we need to know that a 6 is being added here. So we can use the last two numerators to find the next numerator, and the same with the denominators, which gives us our next term. And the product of these is quite close to root 50. So this gives us a pretty good method of finding approximations for root 50, but the output is just a sequence of fractions. This is still not a satisfying result. We'd like the output to be a continued fraction, and here now I'm writing it with p's for product. So how can we get something in this form? Well, going back to this sequence, we notice if we take the floor of each, aside from the first, they're all 7. So this seems to suggest that the floor of root 50 is also 7. And so maybe we could take 7 as that first term. But how do we know for sure? We'll want to notice that this sequence goes back and forth, being below and above root 50. And the same thing happened with the sequence for root 5. We went back and forth below and above root 5. And for any continued fraction a, the even terms approach from below and the odd terms approach from above. So any two consecutive terms define a range that contains a. And so if we have this range for a and another range for b, then assuming that they're both positive, we also have a range for their product. So these two terms in our sequence are consecutive, which means that root 50 is between them. And because they both have a floor of 7, root 50 must also have a floor of 7. So we can confidently say that the first term is 7. But where do we go from here? How do we find the next term, p sub 1? To find that, we'll want to focus on this section here. We no longer need to worry about the 7. And so to do that, we need to subtract 7 and take the reciprocal. So if we do that with each of the terms in our sequence, subtract 7 and take the reciprocal, then we can take the floors, and we notice that the last two are 14. So we have two consecutive terms with the same floor, so that 14 must be the next term. But to find the following term, we need to take each of those and subtract 14 and take the reciprocal. And you can see as we keep doing this, this expression is just going to get more and more complicated. So maybe we'd like a simpler way of doing this. Let's suppose we have two terms in this sequence with the same floor. Then we can take that floor to be the next term in the product. But to find the following term, we'll need to subtract that p and take the reciprocal from each of these. But after we've done that, what if their floors don't agree? We then need to find the following term with j plus 2. It would be nice if we could go directly from these two to the next one without having to worry about subtracting p and taking the reciprocal again. And it turns out we can do this. We just need to rework the method a little bit. So we'll recall that we can split a sub j into a numerator and denominator, and then we can find the numerators and denominators using a recurrence relation. So if we have our product, we can split a and b into their corresponding numerators and denominators. And for now, let's just look at the numerators. Let's rewrite this using the recurrence relations, and then expand everything. And we notice these three all look the same. It's an NA times NB with the same index. So maybe we can call this big N. Now this section looks similar to the recurrence relation for little n, but we also have this other section here that's being added. So how do we deal with that? The terms here are also NA times NB, but the indexes don't match. On the left, the A has an index 1 higher, so we'll call this big NA, and on the right, big NB. And we can also find a recurrence relation for these. Let's look at big NA. If we split little na using its recurrence relation and then distribute, on the right we have big N, and on the left, big NB. So we can use this to calculate NA, and we can just swap the A and B to calculate NB. And so we can take these relations, along with the one from before for just plain N, and now we can calculate these three values. We just need the A and B terms. And we can do something very similar for the denominators. The relations are basically the same. And we notice these are all very nice because they don't have any multiplication of n's with each other or d's with each other. The only multiplication is scalar by a or b. And this will be very useful to let us find the next term without having to subtract p and take the reciprocal again. So let's take another look at this transformation going from ab to 1 over ab minus p. We can replace that ab with n over d, and then if we multiply the right side by d over d, we get this expression. And we'll define this to be our new numerator and denominator. We'll call these n hat and d hat. And we can continue the calculation using this n hat and d hat without any problems. The recurrence relations from n will still work with n hat because n hat is just d, and the recurrence relations for d were identical. So when we find a new p term, we can just take the denominators as the new numerators. But what about d hat? Will the recurrence relations for d still work for d hat? Let's just use the top one as an example. D hat is n minus pd, so we'll replace that everywhere. And then rearrange this a bit, and we see on the left, this is just na, and on the right, this is just dA. And so if we bring that p down, then yes, these two are equal. So the relation for d hat a is the same as dA. And we can show that similarly for the other two. So when we find a new p term, we can just replace the denominators with these expressions and then continue. And so this gives us a method for finding the product of continued fractions. At any given step, we check to see if the floor of the last two terms are equal. If they are, we take that floor to be the next p term, and then perform that transformation, and then check again. If they're not, we find the next set of n and d values, and then increase j. And then we check again. So let's take a look at how this works for our starting problem, root 5 times root 10. We use the two inputs to get our a and b values, and then to fill in the rest of this table, we'll take our first few terms. We can get n by multiplying the numerators, and then na by doing that diagonally, and nb similarly. And then we perform the same thing to get the d terms. Now, we compare the floor and see that they're not equal, so we need to get the next row, where j is 2. So we can find the next n using the recurrence relation. We'll substitute all the values, and this equals 4,446. And similarly, we can find the rest of the values. Now we won't need this top row anymore, so we can just get rid of it and shift everything else up. And then when we take the floor, we see that they now match. They're both 7. So the first term of our product is 7. And now because we've found a term, we need to perform that transformation. So for our new rows, we'll take the denominators, and they become the new numerators. And then to find the new denominators, we take the numerator minus 7 times the denominator. And we'll do that for each of these terms. Now we don't need the old values, we'll just use these new values. And we see that the floors don't match, so we need a new row. So we'll find our next row, just like we did before, and then shift these up. And we see that now the floors do match, they're 14. So we can take 14 as our next term. And if we continue this process, we'll see that the following term is also 14, and then again 14, and then again 14. And now we kind of get a sense of what this continued fraction is. And it turns out if we take 14s all the way down, This does equal root 50. So we've now found our result, root 50, as a continued fraction. And to do this more generally, we can start with this set of values and then just perform that process. But instead of this set of values for j, 0, and 1, we could go back to j, -2 and -1, and instead get this set of values, which is so much nicer. But we want to recall we had a range for a and b, but applying that range to ab only worked if we had a and b both positive. If a and b are both negative, this will still work as a range. We just have the signs flipped. But we run into a problem if their product is negative, if only one of them are negative. Then this range doesn't work. And that's because if we take the absolute value, one of them is going to flip. But there's an easy fix to that. We can just make our range by offsetting the b values. So we'll multiply where b has an index 1 higher. So our sequence will be a sub 0, b sub 1, and then a sub 1, b sub 2, and so on. And we can do this pretty easily. We had this set of starting values for positive multiplication, and we can just change them to do negative multiplication. The entire process remains the same, we just start with different values. And this idea of changing the starting values is also really useful for other operations, such as division. To perform division, instead of multiplying the numerators and the denominators, we can flip those b terms and we'll now be dividing by b. And so we'll define the top as our new big N and the bottom as our new big D. And all of the relations for those will still just work the same. We just need to use this set of starting values for positive division and this set for negative division. The same thing goes with these values for addition or these values for subtraction, which gives us these starting values for addition. And notice the sign doesn't matter because addition never changes inequalities. And we get these values for subtraction. And again, only one set of values because subtraction always changes inequalities. So now we can use this method to do any of those 4 operations. But we still need to cover the question of when do we stop? When we're working in decimal, it's pretty easy to tell how close we are. If we approximate root 50 to 6 digits after the decimal point, then we know that the error is less than a millionth. But with a continued fraction, it's not quite as clear. If we have some result down to the kth term, how do we know how close we are? Well, the true value will have that p sub k plus some 1 over q. And continued fractions are defined to only have positive terms, except for maybe the first. So this 1 over q is going to be between 0 and 1. So if we just take that to be 1, we get a sort of upper bound. And the difference between these two bounds gives us an error term. So we just need to calculate this difference to know how close we are. Or at any given step, we can get even closer if we incorporate our most recent n and d terms, which gives us this error term, which is smaller than the one from before. But this has the downside in that the last handful of terms might not be accurate. And we can think of this as if we were trying to approximate pi. 3.141 has all correct digits, but 3.14162 is closer to pi. So both of these approximations have their merits. The one we choose just depends on what we're looking for. And similarly, we can use this approximation to get all correct terms, or this one to get a closer result. It just depends on what we're looking for. But we need to be careful with the left approximation because this depends on finding terms. We need to actually have some of those p terms to get an approximation. And we can't just take that for granted. Take, for example, this multiplication. This is root 5 times root 5, so the answer should be 5. But as we continue this process, the lower bound will always have a floor of 4, while the upper bound will always have a floor of 5. So the floors will never agree and will never get any terms. But we can kind of patch this. We could say, if the difference between those bounds is sufficiently small, then just assume that the result terminates with the floor of the upper bound, which theoretically isn't great, but it kind of fixes that problem. And speaking of terminating, what if one of our inputs terminates? For example, what if we want to multiply 2 times root 5? We can do the first step in our process, but then we'll run out of terms for that 2. So what do? This isn't a problem working with decimals, because we could just write 2 as an infinite decimal, just using infinite zeros. But that doesn't really work with continued fractions. There isn't really a way to do that. We'll need to adjust the method. So if our a terminates at a sub I, then any further numerators and denominators will just be the same as the ones from index I. We just carry forward the same terms. So going back to our NA times NB, if A has terminated, we only need to worry about splitting B using its recurrence relation. And then if we distribute that, we can subtract 1 from the indexes on NA, because they'll just be the same as the prior value. And now using our big N notation, on the right we have big N, and on the left we have big NA. Or, taking a step back, if N terminated 2 or more steps ago, we could also change that to a -2, and then we just get big N. And so now this recurrence relation is just the same as the one for normal continued fractions. And we'd get the same for the denominators. So we can just use this 2 steps or more after A terminates. And similarly, if B terminates, we just switch those to A's. Now, if both A and B terminate, then we can just stop and use our most recent values, because they both have a finite representation, and so we've just calculated the exact value. So now we know what to do in each of those cases. And so we can go back and finalize our process. At the beginning, we just need to set starting values based on the operation and sign. And then if the terms don't agree, we find the next set of N and D values using the appropriate recurrence relations, depending on which A and B have terminated. And there we are. This process lets us do arithmetic with continued fractions. And this process is not quite as nice as using decimals. It's still pretty tedious to do by hand, which is why I wrote some terrible Python code, which you can find at my GitHub linked in the description. Now, I created this process because I was curious. Could you do arithmetic with continued fractions? But I'm certainly not the first person with this idea. Ali Streetcars and Things has made a video about a different method that explores this from more of a computing standpoint, discussing linear algebra and using continued logarithms instead of continued fractions. So if you've enjoyed this video, you should check that one out too. And this is very useful for, and this will be very useful to let us, and this will be very useful to help, and this will be very useful in that, fuck.